Hello, my name is Subarav. Welcome to lecture on number of integral solutions of linear equation with unit coefficient. This is one of the pretty interesting topic in permutations and combinations. At the same time, some students feel hard to differentiate the cases while applying in general questions. I assure you this lecture will give you in detail overview on integral solutions. At the end, example will give you completeness to your learning about this topic. So let's start to have gorgeous learning experience in this topic. The first point is positive integral solutions of x1 plus x2 plus x3 plus and so on plus xr is equal to n, where r is less than or equal to 1. Before we go to this general equation, first of all, we understand a positive integral solution of a simple equation, which is x plus y plus z equal to 5. Later, we will generalize the what we learned through this example. In this case, I will consider 5 ones. 1, 2, 3, 4, 5. For this, I prefer plug method. We do understand these possibilities for x, y, z with an interesting way. That is nothing but the plug method. What we do in this case, in order to partition the 5 ones into 3 groups, we need two separations. The two separations will make these 5 ones into 3 groups. So that's why I need two blacks. I need two blacks. So this is one, and this is another flag. So how can these flags will help us in order to get the solution, integral solutions of positive integral solutions of this equation x plus y plus z equal to 5. So for it, let me elaborate 1, 1, 1, 1, 1. For example, there are 4 places here. I kept one flag here and one flag here. So this here, the number of flags before, the number of ones before first flag, 2. Number of ones in between these two flags, 2. Number of flags after second, number of ones after second flag, 1. So it means x is equal to 2, y equal to 2, and z equal to 2, z equal to 1. Meaning x is nothing but number of ones left side of first flag or before first flag. Y is number of ones in between first and second flag. Z, number of ones after second flag. So this is the method what we are using in order to count the different possibilities of x, y, z, such that x plus y plus z equal to 5. So let us discuss a few more cases. According to the second example, if I kept the flag here, and this is one more flag, here the corresponding values of xyz according to this case are 1, 2, 2. So then there is a doubt. If I keep the flag here, 1, 1, 1, 1, one more flag here, and 1. So the number of ones before the first flag 0. Number of flags in between first and second 4. After second 1. So this is not desired solution. Why? Because we are looking for positive integral solutions. X, Y, Z each is greater than 0. So this is not possible case. So that means what you can understand, when you have 5 ones, 3, 4, 5, there are only 4 places in order to partition these 5 ones into 3 groups, such that each group contains at least 1 1. So there are only 4 places. So the number of different positive integral solutions of the equation x plus y plus z is nothing but selecting 2 places in order to keep 2 flags out of these 4 possible places. So that means that can be done, as you know that. So just a selection of the 2 places that can be done in 4C2 ways. See how beautifully this concept is related with the flags. So I sincerely thanks to creator of this method. So in general, so at the same time 4C2 you can relate with the 4, total 5 ones are given, 5 plus 3 places, I mean 3 variables. 3 variables. So here 4 can be expressed as a 5 minus 1c, here 3 minus 1. So when you have 3 variables involved in the equation, that means you need 2 flags. So then that is 3 minus 1. Suppose 4 parameters are involved, then we need 3 flags. So that is 4 minus 1. So in general, you can write it as, in this case, you can write it as a 5 minus 1, C, 3 minus 1. So as you know, 4C2 is a 6 ways. As it is a simple number, you can just observe the cases. It can be 1, 1, 3, 1, 3, 1, 3, 1, 1, and at the same time 1, 2, 2, and as you arrange them 2, 1, 2, 2, 2, 1. Okay, so these are the 6 different cases. So when you generalize this concept with when R variables x1, therefore when you generalize it to x1 plus x2 plus x3 plus and so on plus xr is equal to n, we will have n ones, and we need R variables whose sum is equal to n. So in order to get R partitions, we need R minus 1 flags. So R minus 1 flags. So when you arrange n ones, 1, 2, 3, and so on, 1, 2, 3, and so on. So then n ones. So in between these ones, you get n minus 1 places. Out of these n minus 1 places, we need to keep R minus 1 flags. So that means the selection of R minus 1 places out of n minus 1 empty places in between these ones. So that can be done in n minus 1 C R minus 1. So this n minus 1 C R minus 1 is nothing but number of positive integral solutions of an equation x1 plus x2 plus and so on plus xr is equal to n, right? Number of positive integral solutions of this equation, that is n minus 1 cr minus 1. So now the second case. Coming to the second case, now this time we are going to learn about non-negative integral solutions of x1 plus x2 plus x3 plus and so on plus xr is equal to n. Here also r parameters being added and sum is n. This model is a little bit different when compared to previous one. For better understanding, again, let's take simple example and see in-depth solutions, how in-depth how solutions are formed in this case. So let us consider again an equation like this: x plus y plus z equal to 5. Basically, to solve such equations, it is more difficult to find the possible cases manually where there are more parameters and a bigger number instead of 5. So 5 you can calculate easily. You can see the possible cases like 1, 2, 2, 1, 1, 3, 0, 0, 5. Like that you can calculate the cases. When instead of 5, a bigger number is given, more number of parameters are being added, it is very difficult to calculate manually. So that's why we remodel it into another equivalent type of easily solvable combinatorics problem, which is counting the number of possible arrangements, possible combinations in the following string instead of lag method. A little bit different in this derivation. So what it is, so I have taken a string. So what my string is here, 0, my string is 0, 0 and 5 ones. Instead of 2 flags, I have taken 2 zeros. Let me explain you how this string will help us in order to find non-negative integral solutions of this equation. So that means here each x, y, z can be greater than or equal to 0. Whereas in the previous case, x, y, z greater than or equal to 1. Suppose there is an arrangement of this string as 0, 1, 0, 1, 1, 1, 1. So here I consider number of ones before first 0. Number of ones before first 0, that is 0. That is assigned to x. Number of ones in between 2 zeros, in this case 1. Number of zeros after second 0, 4. So 0, 1, 4. It can be a solution of the equation x plus y plus z equal to 5, subject to the condition x, y, z greater than or equal to 0. Suppose let us consider one more case: 1, 1, 0, 0, triple 1, 3 ones. In this case, number of ones before first 0, 2. Number of ones in between 2 zeros, 0. Number of ones after second 0, 3. Corresponding solution is 2, 0, 3. Let me consider one more case: 1, 1, 1, 0, 1, 0. In this case, 4, 1, 0. So by observing these examples, what we can understand, you can see that the answer of the number of arrangements of the string is actually the answer for the number of integral solutions of the equation. So arrangement of string. So what you can write, number of, shall I make a statement like this? Number of arrangements of the string of the string 0, 0, 1, 1, 1, 1, 5 ones is equal to exactly number of non-negative integral solutions. Non-negative integral solutions of x1 plus x2, here xyz, x plus y plus z equal to 5. So therefore, when you consider number of arrangements of the string, there are 7 objects, 7 factorial, in which 2 alike of one kind, 2 factorial, 5 alike of another kind, 5 factorial. So you can write it as by using combinatorics notation N7C2. 7C2 can also be expressed as 5 plus 3 minus 1 C 3 minus 1. The sum of the parameters is 5 and the number of parameters 3 minus 1 C 3 minus 1, right? So similarly, in general, we can observe if you apply the same logic on R parameters, whose sum is n, then number of non-negative integral solutions, is equal to n plus r minus 1 c r minus 1, because you will have n ones and so on 1 n times, and in order to partition into r we need r minus 1 zeros, 0, 0, 0 and so on 0. This is r minus 1 times. So these r minus 1 zeros will make a partition of r among n ones, right? So finally you will get n plus r minus 1 c r minus 1. This is also pretty good method and it's a very interesting, instead of calculating manually, and in fact it is a very difficult to calculate manually one after another, but the simple idea gives entire combinatorics of this summation. So next point is, so far what we have learned, number of positive integral solutions and number of non-negative integral solutions. The next point is the recapitulation or mapping this mathematical concept into general situation. That is, the number of ways in which n identical things, suppose there are n identical things like n ones, can be distributed into all different groups is n minus 1 cr minus 1, under the condition blank groups are not admissible. So zeros are not considered. So that is nothing but positive integral solutions. So as a mathematical model, positive integral solution is related to distribution of n identical objects into r different groups. So that is n minus 1 cr minus 1. If blank groups are admissible, then that is nothing but a non-negative integral solution. Here n identical things into r distributed into r different groups, that is n plus r minus 1 c r minus 1. So these are the 2 points what we have covered so far. If we extend this idea to n distinct things, then what could be the result? N identical things are used in previous 2 examples. Suppose instead of n identical things, n distinct things are taken. At the same time, you want to distribute n distinct things into R groups such that blank groups are admissible, blank groups are not included. So in that case, what you can say, directly we can understand, when you have n different things, when you have n different things, you arrange n objects. Suppose there are n objects like x1, x2, x1, x2, and so on, xn. So let them arrange. So then x1, there is a one arrangement, x1, x2, and so on, xn. In first case, blank groups are not admissible, then we will keep r minus 1 flag. Suppose there are two flags. This is one flag and this is another flag. Only two flags into two groups. Sorry, three groups. Then x1, x2 comes into first group, and x3 to xn minus 1 comes into the second group. Xn comes to third group. Suppose if I make an arrangement like x2, x3, x5, and so on, x1, xn, something like that. If I keep one flag here, first group contains x2, x3, x5, and second group contains some other elements, and third group contains some other elements. So that means first in each case, we arrange all n distinct objects. After that, we proceed exactly how we have proceeded so far in previous two methods. So in that case, you can say n factorial into n minus 1 c r minus 1. So this is if the blank groups are not admissible. So then n factorial into. So here you need to observe the most important point, n different things, that is one keyword. The second keyword is arrangement. When compared with the previous one is a just distribution. That means it's a combination, selection. Whereas in the second example, it comes under the arrangement. Not only selection, we are arranging. See, you see x1, x2 in this example. So x2, x1 is different from this x1, x2. So not only selection, after the selection, we are arranging them into groups. So these are the two key words one must emphasize. Similarly, second case, if blank groups are admissible, n factorial into, you arrange, and after that you proceed as you proceeded in previous method, n plus r minus 1 cr minus 1. All right. So now the third case is n different things can be distributed into r different groups. N different things can be distributed into r different groups. Blank groups are being admissible. First example, n identical things. Second example, n different things. Coming to the third example, again, n different things. Again, it's a distribution, not arrangement, distribution into r different groups. Blank groups are admissible. Whereas in the next one, n different things can be distributed into r different groups. So these last two are much interesting topics in this discussion. So what I can make here, in this case, n different things can be distributed. So I have n objects with me. In order to make you understand easily, I will relate this general concept with functions. Suppose there is a one set here. There are n elements, a1, a2, and so on, an. All are distinct. And b1, b2, and so on, br. It is like groups. Suppose all elements are mapped to b1. Can it be done? Yes, it can be. So blank groups are admissible. So when blank groups are admissible, then all can go to B1 also. So some elements of n will go to B1, some will go to B2, others will go to B3. That is also another possibility. So that means what you can understand, all elements, I mean all distinct elements A1 to n must be mapped with the elements of B1, B2 and so on Br. Suppose the 5 elements are mapped with B1, meaning first group contains 5 distinct elements. Just a distribution, not arrangement here. So this is nothing but, as we know, function. The number of possible mappings of these n elements into r elements of the second set. So that is nothing but r power n. By multiplication theorem, easily you can understand r power n. Whereas in the second example, number of ways in which n different things can be distributed into r different groups, there being no blank group. So that means no blank group. So I cannot leave any number from here. Of course, there must be a condition r less than or equal to 1, otherwise it is not possible. So in that particular case, all elements of the B must be mapped with the elements of the A. Then that concept can be related with our last case. So that is nothing but onto function. So what is the last one? Number of ways in which n different things can be distributed into r different groups, there being no blank group. So once again, I'm repeating the last point. You map these n elements with the elements of r in the second group such that no element in the second set as left. So that is nothing but onto function. Codomain is equal to range. So the last case is related to onto function. The number of onto functions, as you know, suppose if you don't know, then this is one interesting one, number of the onto functions. We will discuss it, the proof using incredible combinatorics result, inclusion and exclusion principle in the next video, right? So finally, you can see the different cases here. Identical things, distribution. Different things, arrangement. Different things, distribution with blank groups. Different things, distribution with no blank group. So these are the cases what we have learned. I hope the point is clear till now. Coming to the next point. So these are the conceptual points in this video. Now let us try to apply these conceptual points in an excellent question. So if you can understand this question with the different possibilities, so completely we can comprehend each and every point related to integral, positive integral and non-negative integral solutions in general. So let us see. There are 5 balls and 3 boxes. The first question asks, how many ways 5 balls can be distributed into 3 boxes? If balls are identical, boxes are different. When blank groups are allowed, blank groups are not allowed. 2 points are involved. In second question, balls are identical, boxes are also identical. Blank groups are allowed, not allowed, as usual, 2 cases. Third point, balls are different, boxes are different. When blank groups are allowed at the same time, I mean, in second case, not allowed. Balls are different, boxes are identical. When blank groups are allowed, not allowed. So these are the different possibilities what we have explored till now. If you can answer this question in all possible ways, then this idea will give a completeness to this integral solutions topic. So let us start doing this question. Direct formula application as well as general case also. Since it is a small number, it will give in-depth understanding of how these formulas are working. The first point is 5 balls can be distributed into 3 boxes. Balls are identical, boxes are different. So that is nothing but distribute 5 identical objects into 3 distinct groups, 3 different groups. So what it says, when blank groups are allowed, first case, blank groups are allowed, blank groups are allowed. So this first question comes under identical things, identical objects into distinct groups, identical objects into distinct groups. So what it says, this is nothing but positive integral blank groups are allowed. So non-negative integral solutions. When blank groups are not allowed, that would be easy in the first case. Blank groups are not allowed. This comes under positive integral solutions. As we know, it is n minus 1 cr minus 1. In this case, 5 minus 1 c 3 minus 1. So that is nothing but 4c2. 4c2 is 6. So blank groups are not allowed. So in general, this is a direct application. I want to see how these 6 cases are coming out. The possible cases, divide 5 into 3 groups, that is 1, 1, 3 and 1, 2, 2. There are only 2 possibilities. So this 1, 1, 3 should be given to 3 distinct groups. So that means this can be arranged into distinct groups 3 factorial ways. 3 factorial by 2 factorial, since 1 and 1. So then you can write 3 ways only. That is otherwise 1, 3, 1, 3, 1, 1. Similarly, 1, 2, 2 can be arranged themselves in three ways. So then 3 plus 3 ways. This is how it is happening 6. Okay. Now again, the second part of the first question is, blank groups are allowed. Blank groups are allowed. When blank groups are allowed, what you can say, identical objects into distinct groups when blank groups are allowed. That is n plus r minus 1 cr minus 1. This is 5 plus 3 minus 1 c3 minus 1. That is 7c2. 7c2 is 7 into 6 over 2 into 1. So that is 21. So as it is a small number, we can manually calculate the cases. So let us check, let us have how these 21 cases are coming out. 1, 1, 3 is one case, and 1, 2, 2 is other case, and 0, 0, 5 third case, and 0, 1, 4 this is another possibility, and one more possibility 0, 2, 3. So these are all 5 possibilities. As we know in the first 2 cases, 3 plus 3 ways. And third case 0, 0, 5, that can also be done in 3 ways, 0, 0, 5, 0, 5, 0, 5, 0, 0. And whereas in 0, 1, 4, it's not in 3 ways, it's a 3 factorial ways. And whereas in 0, 2, 3 can also be done in 3 factorial ways. So then 9 plus 6 plus 6, this is nothing but 21. So how this formula is working, this formula itself calculating all the possibilities. Next, coming to the second point. I hope this point is clear to everyone. Now second point, balls are identical, boxes are also identical. Balls identical, boxes identical. Such case is not discussed previously. So now in that cases, we need to calculate manually. So first case, blank groups. Blank groups are allowed. When blank groups are allowed or not allowed, blank groups are not allowed. When blank groups are not allowed, what you can say, 1, 1, 3, same example, 1, 2, 2. When all boxes are also identical, there is only one way of keeping these identical balls in three groups, 1, 1, 3. So this is only one way, and this can also be in one way. So 1 plus 1, this is two ways. When blank groups are allowed, as we know, 1, 1, 3, 1, 2, 2, and 0, 0, 5, 0, 2, 3, 0, 1, 4. So these are the 5 possibilities. In each possibility, we can get only one way of distribution. So that is 5 ways. So when blank groups are allowed, balls are identical, boxes are also identical. So then there are only 5 cases. Blank groups are not allowed, then only 2 cases, right? So coming to the third point, balls are different, boxes also different. Balls different, boxes different. In this case, third point, balls different, boxes different. Balls are different, boxes are different. Boxes are different. Blank groups are not allowed. Blank groups are not allowed. Are not allowed. So this is the last point of previous discussion. That is nothing but onto function. So this is onto function. Number of onto functions. Number of onto functions. Okay. So as for number of onto function, the formula is 3 power 5 minus 3c1 into 3 minus 1 power 5 plus 3c2 3 minus 2 power 5, which is 243 minus 2 power 5, 32, and 3c1, 3, 96, plus 3c2, 3, 1, 3, 1 jar 3. So 246 minus 96, 150. Okay. So as for a last application. Suppose as it is a small number, if you want to calculate manually these cases, that is also interesting, so that you can get a better way of understanding while you are learning about the difference between the cases. 1, 1, 3 and 1, 2, 2. Blank groups are not allowed. So meaning what we need to do, different objects, 5 different objects must be distributed into 3 groups in which 1, 1, 3. Number of objects in each group are 1, 1, 3. So in the second possibility, 1, 2, 2. So first let us make them into the groups. So division into groups. So as for the division into groups, what you can write, 5 factorial by number of objects in first group 1 factorial, second group 1 factorial, third group 3 factorial. As we know, there are 2 groups which are having equal number of objects. So we need to write 1 over 2 factorial. That means we have made the balls into the groups. That means we have made the balls into 3 packets. So these 3 packets must be arranged into 3 boxes. Here 3 different boxes. So how many ways can you arrange three different boxes, three different parcels or packets into three boxes? That can be done in 3 factorial ways. So that means a total 5 balls are there. There is a earn 5 balls are there. So we made them into the 3 groups. So this is one packet and this is another packet. This is a third packet. So these 3 packets must be arranged into 3 boxes. So 1, 1, 3 all are different. So 3 factorial ways. So this is the first step. This is a division. Next, arrangement into the boxes. So these are the general situation how it is happening. So again, coming back to the second case, 5 factorial by 1 factorial, 2 factorial, 2 factorial into, here also 2 groups which are having equal number of elements. So that's why 1 by 2 factorial grouping is done. Then arrangement, again it comes under 3 factorial. So if you simplify this, 5 factorial, 3 factorial got cancelled here, 120, so 60 by 2 plus 2, 3. So 3 factorial, here 2 factorial goes into 3 factorial exactly 3 times. Right, here 4, 5 factorial, 120. So finally 30, 33s are 90. So this is 150, 150. This is general way. This is direct application. Okay. Now, when blank groups are allowed, next, second case in third point, blank groups are allowed. When blank groups are allowed, then it comes under number of functions. Number of functions. The second from the last. So in our point, second from the last. So that is 3 power r power n. R power n means 3 power 5. 3 power 5 is 243. 243. Okay. So if you want to calculate how this 243 manually, since it is a small number, we can go in detail. So what is the first possibility? 0, 0, 5. 0, 0, 5 is only one way. Only one way we can distribute the objects. Then afterwards, we need to arrange them into 3 distinct boxes. There is only one packet, 0, 0, no packets, no balls. So only one packet. So 3 boxes, only 3 ways. Next, 0, 1, 4. When 0, 1, 4, that is first division into groups, 5 factorial by 1 factorial into 4 factorial. Afterwards, 3 factorial. 3 packets into 3 boxes, 3 factorial. So then what you can write for 5, here 6, 6 5s are 30. The next case is 0, 2, 3. When 0, 2, 3 grouping is 5 factorial by 2 factorial into 3 factorial. Again 3 factorial. So 3 factorial, 3 factorial will get cancelled. 120 by 2, it comes as 60. Plus not blank groups. So that already we have calculated in previous case, that is 150. 150 plus 93, this is 243. So how it is coming out? I hope this third point is much clear. Once let me show you the third point. Okay. The balls are different, boxes are different. Blank groups are allowed, then it is number of functions. Blank groups are not allowed, then it is undo function. Now, the last point is balls are different, boxes are identical. Balls are different, boxes are identical. Coming to the fourth case, fourth point. Boxes are identical, balls are different. Balls are different, boxes are identical. Blank groups are not allowed. Blank groups are not allowed. Then we can make it into 1, 1, 3 as it is the first case, that is grouping 5 factorial by 1 factorial into 1 factorial and 3 factorial into 1 over 2 factorial since equal number in first two groups. So this is equal to 5 factor 120, 5 4 is 20 by 2, that is 10 ways. So there is no arrangement of these groups into three distinct boxes since all boxes are same. No difference. Coming to the next case, 1, 2, 2. 1, 2, 2 again, it's a just grouping only. 1 factorial, 2 factorial, 2 factorial, and 1 over 2 factorial. Again, it comes as a 15. This is 25. That's 25. Right? Yes, blank groups are not allowed. So the same way, directly you can answer this question. So how can you answer this question? When boxes are also different. Balls different, boxes different. When balls different, boxes different, blank groups are not allowed, then what you will get, number of onto functions. Number of onto functions. Number of onto functions by number of onto functions by number of boxes. Number of boxes factorial. Number of boxes factorial. Number of boxes factorial. Because there is no arrangement. So arrangement is not required when boxes are identical. So whereas in number of onto functions, we are making them into groups. After making them into groups, we are arranging them into the boxes. But whereas in the last case, boxes are identical, so no need of arrangement of packets into boxes. So that's where that factorial will come. So similarly, what we can write here in the previous example, number of onto functions, let me verify for you, 1 by 150 number of onto functions by 3 factorial. 3 factorial. So this is nothing but 150 by 6. Right? So this is nothing but 25. So you can directly proceed when balls are different, boxes are identical, like directly number of onto functions by number of boxes factorial, number of groups factorial, right? So coming to the last point. In the last point, balls are different, boxes are identical. Just we need to calculate 3 other cases. So in these 3 other cases, let me add 3 more cases. In addition to these 2 cases, we need to add 2 more cases. What are the cases need to be added here? Blank groups. Blank groups are allowed. Blank groups are allowed. In this case, in addition to this 25, 0, 0, 5, 0, 0, 5, 0, 1, 4, and 0, 2, 3. So 0, 0, 5 is only one way, and 0, 1, 4 is 5 factorial by 1 factorial into 4 factorial plus 5 factorial by 2 factorial to 3 factorial. So 5 factorial by 4 factorial, that is 5. Coming to the last point, 5 factorial over 2 factorial into 3 factorial comes as a 10. So this is 26. So total 51. 26 plus 25, 51. When blank groups are allowed. So the total cases. So these are finally all these examples will give us a complete idea. So let us finish this session with the last example. That is, 5 different balls can be arranged into 3 different boxes so that no box remains empty. The last example is 5 different balls. 5 different balls can be arranged into 3 different boxes so that no box remains empty. No box remains empty. Empty boxes are allowed. These are the 2 cases. Empty boxes are allowed. Try to understand and relate with the previous concept. The keywords are arrange, different balls and different boxes. As we observed in the first question, theoretically, this is n factorial into no box remains empty, n minus 1 c r minus 1, which is equal to 5 factorial into 5 minus 1 c 3 minus 1. So that is 120 times 6, which is nothing but 720. Whereas in the second case, n factorial empty boxes are allowed, that is n plus r minus 1 c r minus 1, which is 5 factorial into 7c2. So finally, let me explain you just the first case, how it is coming out in 120, so that you can clearly differentiate with the previous cases. So as I'm repeating, as I emphasized previously, again I'm repeating here, the key word in this question is, for this understanding, the key word is arrangement. So arrange into 3 different boxes, whereas in the previous cases, it is just distribution. In this case, it is arrangement. So let me tell you to calculate the cases individually. So what it is happening, how it is coming out 720. So in this case, 113, first case, I'm calculating manually, 113 and 122. These are 2 possibilities. So what we need to do here, first 5 objects, make them into groups 1, 1, 1, 3, and keep them into boxes, arrangement into boxes. And after choosing the boxes, then again you will get the arrangement of boxes, I mean objects into the boxes. Like, so this is a 1 red ball, and this is a 1 red and blue ball. It's a different from this way. Blue, we need to arrange these balls into the boxes. So this is different from this arrangement. So this is the extra step when compared with the previous cases. So let me write you to understand more clearly. 5 factorial, first grouping. So first grouping. So that is 5 factorial by 1 factorial into 1 factorial into 3 factorial and 1 over 2 factorial. Grouping is done. When grouping is done, now we need to arrange these groups into the boxes, groups and boxes. We need to select the box to keep these groups. So that is can be done in 3 factorials. Till here we did it. Now afterwards, these balls must be arranged in the boxes. So first box will get only one ball, so that is only one way. Second box also one ball. Coming to the third box, we have three balls. So the three balls can be arranged in between them. That is 3 factorial plus 5 factorial by second case, again grouping 1 factorial, 2 factorial, 2 factorial into 1 by 2 factorial, and again grouping 3 factorial. So now coming into the boxes, in order to arrange these balls in the boxes, that is first group only one way, second group 2 factorial, because in second group there are 2 balls. Third group is also consisting 2 factorial. I mean 2 balls, so it can be in 2 factorial ways. So this is the difference. This part is different in this last case. So arrangement, previous one distribution. So when you calculate it, 3 factorial, 113 will get cancelled, right? Next 3 factorial, 2 factorial, 60 plus 3, 6, 360. So this part is, first part is 360. And coming to the second part, this part is 360. Plus 1, 2, 2 factorial, 2 factorial will get cancelled. So here 60, again 60 into 6, that is 360. So 720. So when you divide them into the cases, that what it is happening inside in this 720. I hope all cases are clear. So in all possible cases, the balls are different, boxes are different. Identical, identical. Here different, they're identical. So I covered all possible cases. At the same time, the keywords are distribution and arrangement. I hope this lecture is clear to you. We will discuss number of examples and integral solutions with non-unity coefficients in the next video. Stay tuned to that. Thank you.